push that rock with Simpson math. Let's solve a related rates problem. This problem is taken from James Stewart's calculus textbook. It states, it's for step 1, read the problem. Especially pay attention to the question. So it states, a lighthouse on an island stands 3 kilometers from a dock on a shoreline revolving a beam of light 4 revolutions every minute. How fast is the beam moving when it's 1 kilometer from the dock? Okay, we read it. Now, step 2 is to try to make sense out of it in terms of a diagram and assign variables to the diagram. Sometimes this step's not needed if it's already done step 4 for you, but if step 4 hasn't been done, you're probably going to have to draw a diagram. So I'm going to draw a diagram. We have a shoreline. That's pretty straightforward, and on it is a dock. We have an island, and on it is a lighthouse. And it's shooting out a light that's going around and around, or maybe it's going this way, and at some point it's revolving and the light hits the shoreline, and then there's going to be this light traveling along the shoreline as the beam of light rotates. Okay, so we have a diagram here. Now we want to try to assign variables. Well, we have a triangle. If I could draw a straight line, this should be a straight line. Now, this is a distance of 3. It's always 3, but you generally want to try to keep numbers out of your diagram. But, I mean, if there's a number that's always there, then use it. But this 1 I'm not going to use because it's not always there. That 1 is tied to a moment in time. So I'm not going to use that. But this distance where it is obviously going to be important because at one point in time, the beam is 1 kilometer from the dock. So I'm going to assign a variable to that. Then the other thing that's obviously important is the fact that it's revolving, so this angle. Because it says we're given this information about revolving, so that angle is important. So there I have, and we might label this, I don't think we're going to need it, but you know, if you think this is obviously changing too, so you could call this Z or H for hypotenuse. But I don't think we're going to need it, so I'm not going to worry about it. Now step 2 is done because we've drawn the diagram and we've assigned variables. Now step 3 is to lock up rates and values tied to a moment in time. So we're given a rate. We were told that it's revolving at 4 minutes per, 4 times around per minute. So I'm going to create a little lock box here. It's going to have a keyhole. And I'm going to take the fact that the angle, this angle theta, is changing, and it's going around a full 2 pi radians 4 times per minute. Okay, so this is 8 pi radians per minute. So I locked up that rate. If I had any more rates, I'd lock them up. I also lock up any values, like this x value tied to a moment in time is 1 kilometer, so I lock that up. And maybe we feel like we ought to solve for theta. I don't think we will, but you know, maybe find theta at that moment, and maybe find this hypotenuse at that moment and lock it up if you feel like you might need it. Let's wait and see if we need it. Now, step 4 is to relate your variables. Well, clearly I can use trig to relate a theta to a distance opposite theta. So that would be tangent of theta is equal to the opposite distance over the adjacent distance. So I have a relationship between the variables. That's very key. Make sure you're relating variables, not numbers. If I had a 1 here, well, that doesn't help me any at all. Well, tan theta equals 1/3. We're solving a related rates problem. Okay, so relate variables, that's key. Then the next thing is you're going to implicitly differentiate with respect to time. So the derivative of tangent is secant squared theta, but we're doing this with respect to time, so we throw in a d theta dt, just as if this was a y and we were doing implicit differentiation normally. Here I have a line, it's 1/3 x, so the derivative of 1/3 x is 1/3, but I must throw in a dx dt. You're saying that's an x, normally we leave that alone. Yeah, but it's with respect to time as our variable, input variable, not x. X is an output variable, it's a distance. And we're finding how the rate at which that distance changes with respect to time, so dx dt. Now we're ready to unlock the box. See, we have these things, these dt's running around. See those dt's? When you get those dt's, those are keys. You pick it, there's the handle to the key. You pick it up, you insert it in the lock, you twist, you open the box, and you pull this stuff out. So, for instance, I can put in 8 pi radians per minute. I'm not going to bother with the units, but just think about the units. 8 pi radians per minute. Then over here, I don't know dx dt. That's what I want to know, so I'm going to solve for dx dt. Can I put in something for theta? I don't need to put in anything for theta. I need to put in something for secant of theta. What is secant of theta? When the triangle is a 3 here and a 1 there. Well, we need to know that at that time is the square root of 10. Oh, so secant of theta would be the hypotenuse over the, hopefully you can see this, I'm having to write so small, I'm an idiot and made my lockbox so small. The square root of 10 over the adjacent, which is 3, because this is the angles up here. So this is the hypotenuse and here is the adjacent. So, so there's the angle there. So anyway, secant of theta is root 10 over 3, and I'm squaring that. So I plugged in for secant of theta, and I never had to bother to find theta. But you could have. Been a lot of extra work, but that'd be fine. So now I square this, and I have 10 ninths times 8 pi. And to get dx dt by itself, I'm going to triple both sides. So I triple. And then this gets rid of that, and I have 10 over 3 times 8 pi, and that's dx dt, and there's the exact answer. And to answer the question, we'll think about it. Let's see. 8 times 10 is 80, and 3 goes into 81 27 times. So that's almost 27, 26 and 2/3. Let's just call it 27. So it's about 27 pi. But pi is 3 times 27 gets me back to the 81, but it's a little bit bigger than 27, so a little bit bigger than 81. So I say it's about 84. And what are we talking about here? Well, it's kilometers. I should put my units in. I'll put that in my way. Let's get rid of that. It's kilometers is the output, and the input is minutes. So it's kilometers per minute. That's the rate at which this x distance is changing, the rate at which the beam of light is moving when it's 1 kilometer from this dock and moving that way. Now you might say, well, would it be different if it was over here moving away? I don't actually think so. It'd be a nice symmetrical situation. I think we get the same answer. So there's your answer to the related rates problem, but what I want to point out is the key steps. Okay, I break it down into these steps, but most importantly, you must relate the variables that are in play and then implicitly differentiate with respect to time and then solve for your unknown that's given in the question. Math made simple. Simpson math.